Hi everyone, my name is Mackenzie, and this is the TOIS talk on boosting search performance using query variations. This was work done with Rodger Benham, Alistair Moffat, and Shane Culpepper at RMIT University and the University of Melbourne. So, to start off with, a few quick definitions. Firstly, a multi-query queue is defined as a set of n unique queries, q sub 1 through to q sub n. In the example here, we have a multi-query with three queries. One is benefits of coffee, the second is espresso, and the third is coffee health. And what we're interested in is multi-query fusion, which involves processing each query inside the multi-query to generate a results list, and then fusing these results lists together by some rank fusion algorithm to generate a single results list, which we call R prime. So as a concrete example, consider system X. We process the first query, benefits of coffee, and that gives us a top 3 results list of document A with a score of 3, B with a score of 2, and C with a score of 1. We do the same for espresso and for coffee health, and now what we want to do is fuse these 3 results lists into one single list. A simple method to do so, called COMSUM, involves summing up the scores of each document in each list. For example, the first list, document A, scores 3, so we add 3 to the accumulator for A. We continue with B, and so on through all the lists until we have a final score for each document. We can then sort this vector, and that's our fused results list. We can return this list to the user. We're interested in query fusion because it's been shown to be very effective. The table here shows as you add more and more query variations, essentially as you make the multi-queries larger, effectiveness increases quite a lot. And this was shown all the way back in 1993 from Balkan, who essentially showed the same thing. The more variations, the better the results. In this work, we're looking at the UQV 100 collection from Bailey et al. In SIG-IR 2016. This collection contains 100 topics, and each topic has a number of query variations for each topic, including relevance judgments, over the ClueWeb 12b corpus, which is 52 million English web documents. These user query variations, or UQVs, were collected by showing crowd workers backstories and asking them to submit queries that they thought would help them with this information need. For example, take the topic 290 backstory. Many tree species look alike, and so it's easy to mistake one type of tree for another. Your friend has said repeatedly that they have a Norway spruce growing in their garden, but you don't think it is. You decide to try and identify whether the tree is what your friend says it is. So if you show this backstory to crowd workers, you get back a lot of query variations. The most common of these is Norway spruce, but you also see queries such as Norway spruce images, Norway spruce trees, Norway spruce tree, and so on. So in this work, we're focused on how we can efficiently process all of the queries inside a multi-query and fuse them. So we want to do this as quickly as possible. For this task, we employ all of the unique queries for each topic in the UQV 100 collection, and this is an average of 42 unique queries in each multi-query. So we're going to take these 42 queries, run them, and fuse the results together to get a single list. And we do this with top 100 fusion using the BM25 ranking function and the COMSUM fusion algorithm, which I showed in an earlier example. So just for the examples ahead, assume we have a multi-query made up of 3 unique queries. 1 is Norway spruce, 2 Norway spruce images, and 3 Norway spruce trees. The most obvious thing that might come to mind is just running these queries in parallel, getting the top K results for each and fusing them at the end once all queries have returned results. And we call this parallel fusion. The good thing about parallel fusion is we don't have to change the underlying system. We can just run all of the queries in parallel. If we do this, the fastest method that we found using 56 threads gave a median latency of 133 milliseconds and a 95th percentile latency of 466 milliseconds. However, you might have noticed that a lot of the UQVs contain the same terms. And here's an example of this across 2 collections, one UQV 100 on the right, which is the one we're talking about, but also on a different set of user query variations on the robust corpus. And what this graph shows is that most of the query variations contain at least one or two very central terms. So in our example, most of the query variations contain the terms Norway and spruce because they're very central to the information need. And so we believe that we can exploit this term redundancy such that we're not processing the Norway and the spruce postings list multiple times for different multi-query subqueries. So one approach is to exhaustively process all of the unique terms in the multi-query just once. So now we're not processing Norway spruce postings list multiple times, we're just processing them once. But to do this, we need to store adjacency lists to a unique min heap for each query in the multi-query. And so this is a bit more technical. And the other problem here is that we have to look at every document in every postings list exhaustively. We can't do any fancy dynamic pruning to accelerate query processing. So as you might imagine, this is very slow. So using a single thread, this will take 7 seconds in the median and 95th percentile of 15 seconds. So even though we're only looking at each postings list once now, we're doing much worse than the parallel method. What we really want is the best of both worlds, where we can benefit from dynamic pruning and efficient processing across the query, but we don't need to use a bunch of threads to do so. To demonstrate how this is possible, I've broken down an example of two multi-queries, and what we're looking at here is how we're scoring document A for each query. In the first multi-query, we're going through and we're seeing that document A has an impact of 3 for the term benefits, an impact of 1 for the term of, and an impact of 5 for the term coffee. And what that gives us is 9. So document A scores 9 for the query benefits of coffee. We then run the coffee health query. Coffee again scores 5 and health scores 2, and that gives a score of 7. And at the end, we're fusing those two things together to get the final score of 16. But you might have noticed that because we're looking at the same term in the same document on both of those multi-queries, we're still going to get the same impact score, right? So we've processed coffee twice and scored that twice, where we could have only done it once. So how could we possibly do better? Well, the approach that we took is to rewrite the multi-query into a single weighted bag of words. So where we have these two queries here, we can rewrite as a weighted bag of words. Coffee appears twice, so it receives a weight of 2, and all of the other terms only appear once, and again receive a weight of 1. If we go through and sum up the impact multiplied by the weight, we get the same score. So what we've essentially done is we've rearranged the fusion such that it happens at scoring time rather than later. And this works for all multi-queries. You just rewrite them as a weighted bag of words. For our example before, it would be 3 Norway, 3 spruce, 1 images, and 1 trees. And now what we can do is what we call single pass comp sum fusion. We again only have to process the unique postings, but we can also use dynamic pruning to efficiently traverse these postings lists. And so the best approach using SPCS with one thread, we can get down to 246 milliseconds at the median and 870 milliseconds at the 95th percentile tail latency. So these are 2 times slower than the parallel fusion methods, but they use 55 times less resources. So we see this as a pretty big win. There are some more detailed efficiency results, but I refer you to the paper for those. So in the second half of this paper, we ask a different question. Suppose that we can pre-compute and store some information pertaining to a single information need offline. So what that involves is identifying similar queries that are related, generating results lists for these queries, fusing them offline, and storing them in what we call a centroid C. So essentially, we're offloading this expensive fusion to offline. And so in this example, we have some information need about dark chocolate health benefits. We can mine query logs to find queries that are relevant to this topic, and we can fuse all of those results lists and store them and cache them, right? And now the problem becomes, given an incoming query queue, which we haven't seen before, firstly, can we associate the query to one of these centroids? And secondly, assuming we can do so, how do we combine the results we get from the new incoming query and the cached centroid, which we call query boosting, to give a more effective top K document results list? So a few approaches we tried. The first is called returning the centroid. So in this example, I'm showing C, and that's the centroid that we've computed offline, and I'm showing D. This is the results list computed from the user query. The blue documents in D correspond to those that are in both D and C, and the red documents are those that are in D but not in C. So returning the centroid says, I don't care about D at all, I'm just going to return C, okay? Another approach is to interleave the results, so we draw from D first. So in this case, we would say document 9 is at rank 1, document 1 is at 2, document 2 is at rank 3, and so on. Another approach we tried is reference list reordering. So what we do here is we take documents that are in the intersection of both C and D, we put them at the top of the ranking, but we order them with respect to their order in C. And with the remaining documents from D that were not in C, we append them to the end of the ranked list. And the intuition here is that if we get the centroid wrong, we're still showing some results from the user query. And this is the same for interleaving. It's giving us some results from the user query as well as from the centroid. The final approach we tried is just a simple linear combination over scores. So most people might have seen a linear combination before, but essentially we're just multiplying the score of the document in C by delta, and we're adding that to 1 minus delta times the score of the document in D, and that gives us a final score. And then at the end, we sort all of the documents by their final score, and that gives us a results list. So assuming we can always find the correct centroid for these queries, we see our 4 approaches, RCC, interleave, LC, and ref reorder, they significantly outperform a learning to rank baseline. And this is after doing a family-wise Bonferroni correction. So we're seeing very large improvements here. And again, the LTR baseline is much stronger than the user query BM25 baseline. This figure shows the per query effectiveness differences between each system and BM25. BM25 is shown as a black line. As you can see, both the interleave and linear combination approaches can improve upon the baseline in most cases, but suffer from some small losses as well, which are shown as points below this black line. On the other hand, the ref reorder and return centroid approaches, they have much larger wins, but they also exhibit much larger losses, which means these are more risky systems to deploy. The problem with the previous experiment is that we assumed that we could always match the incoming query to a cluster with no error. We always could find the correct cluster. But in practice, this is unlikely. Similar tasks have been shown to reach precision and recall of about 95% in a similar experiment involving 20,000 clusters. So what we're interested in doing now is simulate assigning queries to the wrong cluster at some rate epsilon and examining how these different approaches fare under some error. And what we do is we run 10 trials with varying values of epsilon between 0 and 1, and we plot the mean outcome. Here's the results with NDCG at 10. The 2 horizontal lines, the black one at the top is the LTR baseline, and the grey one below is the BM25 baseline. The other 4 colours are our 4 approaches. As you can see with returning the centroid, which ignores the user query entirely, it's very effective when you can almost always get the centroid right, but it quickly gets worse, and if you always get the centroid wrong, this approach will give you a score of 0. On the other hand, the other 3 systems are much more robust to error, and in particular, the ref reorder system actually just decays to being a BM25 results list on the user query, as you can see at the orange line with the error rate of 1. So it's very interesting that our other approaches are much more robust to error, and that means that they're less risky to deploy in a real system. So in summary, we proposed a few different techniques for efficiently processing multi-queries, which are queries made up of a number of subqueries. There were various trade-offs between cost efficiency and flexibility. We also show how you can use dynamic pruning and fusion together to do this type of processing efficiently. The second part explored how pre-computed centroids can be used to boost query effectiveness. So we explore how we can combine this pre-computed centroid with the user's query results list, and we show that you can get risk-averse improvements by blending centroids with the user query. There are many other experiments in the paper, so please go and take a look. There will be a virtual discussion on Tuesday the 28th between 12 and 1 Beijing time. Otherwise, you can email me with any questions. The codebase is available and it's based on the PISA search engine and it's on GitHub at this URL. So thank you for watching the talk and I hope you enjoyed it.